So logarithmic functions, graphs, we're going to start with the definition of the parent function and parent graphs. So we have the parent logarithmic function looking like this: y equals log in base k of x, with the same conditions we had for the logarithm calculation. So we cannot have our base there to be a negative number, and it has to be different than 1, so positive different than 1. And then we also have the same condition we had for logarithms, the number under it. So this x has to be a positive number. This is what we always state as a condition when we solve logarithmic equations, right? Because otherwise we can't have those we can have our solutions being negative numbers, and sometimes they do end up to be negative numbers, or whatever the condition becomes, because x here stands as an expression. This is just a parent logarithmic function, but it can be other things as well, right? We cannot have that expression to be negative, and sometimes because our equations became other types of equations, right? We also have to be careful with that, to go back to logarithms and see if now they exist or they don't exist. Here's an example of a parent logarithmic function, log in base 5 of x. Special example, natural logarithmic function, and even y equals log of x, which is the base 10 logarithmic function, because these ones don't show their bases. It's important to recognize that all the time, because when you have to sketch it, the base is part of that sketch, okay? A type of the function. And they are different from one to another. How many logarithmic functions that we call parent functions can we have, really, if that k is a variable? Okay, how many can you have? An infinity, pretty much, right? Because if I say k is bigger than 0 and different than 1, right? Basically, I'm listing all of those positive numbers that are different than 1 and positive, right? Which are pretty much real numbers. It can be anything that's a real number in the base there, right? That makes it an infinity of values that k can take, therefore an infinity number of parent logarithmic functions. But they will look different in the way that exactly point for point they look, but in terms of shape, they look very similar. They will be increasing, you'll see, from quadrant 4 to quadrant 1, and we will talk about those trends in a little bit. So a logarithmic function is related to our exponential function by the idea of inverse. So remember in unit 2 what an inverse function did. Do you remember that? How did we know that two functions are inverses of one another? Well, every single one of their points, corresponding points, they're vice versa of each other in terms of values, right? So if your original function had xy, your other function had yx, with the note, like I'm going to put a star beside it, this is still an x coordinate and this is still a y coordinate, just the value is just the vice versa value, right? So logarithmic functions and exponential functions will have that relationship between themselves. This is like fancier way of writing this property, is if you have an inverse of the function, it's called g of x, then you're going to get x, okay? So if you're plugging in the y into the function, you're going to get the x, okay? And vice versa, if you're doing the other way around, g to the -1 of f of x, it will give you the x of the other function, okay? So this is something that we've used a lot in sinusoidal function, because we had to apply sine inverse, right, to the value, which is 1/2, and then we got the input of the function sine of x, which is 30 degrees, right? Let's do the degrees, it's a little easier, right? Because all it says is that sine of 30 degrees is 1/2. So it takes out, it does this x. Maybe I should put the f of x here because we use the sine, which is the same function, but that's pretty much what it does. Okay, let's do some examples so we can deduct the shape of our parent logarithmic. Since we are familiar already with exponential functions, we can use that approach. This is the function 2 to the x, which has y-intercept at 1, so 0, 1. And the next point that we took for our parent function was the point that is x equals 1, and then evaluated for the base, right? So 1, 2. And the function looks like that with a horizontal asymptote. The next point would be 2, 2, and 4, right? So if you choose x is 2, choose the 2 would be 4, and so forth. Okay. Now we remember again from unit 2, changing those x's and y's in terms of values, all it does graphically for the new function, the new inverse function, is a reflection along this or about this axis called the y equals x-axis. If you were to graph this function, this linear function, y equal x, that's the line you would get, right there, cutting it exactly half diagonally, quadrant 1 and quadrant 3. So then the point that was originally 0, 1 becomes the point 1, 0. So just flips over. And the point that originally was in the exponential function 1, 2 becomes 2, 1. So we have this graph that increases very fast. So fast here between 0 and 1. When I choose my x's between 0 and 1, it goes really, really fast from one point to the next. And then after it crosses the x-axis at the intercept, the growth of that function is not so steep anymore, not so fast anymore. So the rate of change is slower here. Now, if I want to see these 2 points in a table of values, well, all you would do is draw your table of values. Our function log in base 2 of x is there, so it's a function g of x. Now that means I would take this point here, so the x is 1, and I would have to calculate log in base 2 of 1. And we know this because we've done logarithm calculations. So what would that equal to? Not 1. 2 to what exponent? No, not 2 either. 2 to what exponent equals 1? That's what we did to logarithms, right? Which is 2 to what exponent equals 1? 2 to what exponent equals 1?
2.
2 to the 2 is 4. So no. 2 to the 1 is 2. So not 1. 0, that's right. And this is a harder one to remember because it's by definition, right? So you need you need to remember those rules, okay? So this is a 0. That means if I evaluate log base 2 of 1, this input of x, I get 0. So it gives me my first point here, right? In a table of values approach. And then if I do a next point with logarithm, you would have to choose good x's that allows you to calculate the logarithms without the calculator. The next good x choice would be the same as the base, which is 2 in this case. And I would do log in base 2 of 2, which gives you, same question, 2 to what exponent equals 2? 1, right? So now you would get the 1. And then if I want to keep going and get the next point, remember the next point was if for the exponential function 2 and 4, right? Now these are backwards. So the next point that I have to choose, the next x choice that I have to do to give me a good opportunity for calculating without the calculator, it would be any power of the base. So 2 to the 2, 2 to the 3, 2 to the 4, and so forth. So the next nice number to calculate would be 4 for my choice of x. So then I would get log in base 2 of 4. And the question in my mind or on paper until I get to that point is 2 to what exponent is 4, which is 2, right? So the point before 2, the next point here. We only work with these 2 points over here because it's just easier. They all look pretty much the same, but I want you all to understand where the shape of that graph comes from. Now, how about the asymptotes? Does this one have an asymptote? Well, yeah, because when you put a condition like this on the inputs of your function, the argument of the function, you're actually putting a condition on the domain of the function, right? You're describing what the domain values could be, right? So you're having all of your x's bigger than 0, there's nothing beyond that. Why? Because they don't exist, okay? It's marginalized here by a vertical asymptote. So as we get closer and closer with my x's to the value of 0, but not as 0 because I can't, the y values are going to negative infinity. That's how we describe in a fancy way the idea of a vertical asymptote. X is the closest value to the location of the asymptote, and then the y is going to infinity. Okay. Now let's graph e to the x, just to see again that relationship really quickly. We always have this cross at 0, 1, and then 1 in e, which is 2.7-ish. And then our logarithmic natural function is switching those points, coordinates. So we're gonna have the x coordinate at 1, and the next point is at E1. Fill in here, this is the ln of x function. And this one here, make sure everybody understands, is log in base 2 of x function. So we notice again the same growth between 0 and 1, really steep growth there, fast rate of change, and then after it crosses over at 1, the growth is not as steep. And all of the characteristics, we notice that we have an asymptote at x equals 0, so go straight through that. And then we know that we do have an x-intercept in the situation, but because we don't cross the asymptote, we don't have any y-intercept. Domain x bigger than 0, and the range, all of the real numbers, right? Top and bottom, it keeps going. For the purpose of graphing, you can memorize these 2 points. So for any parent logarithmic function, we always take the x-intercept as a point, so 1, 0. And the next one we take is the base and 1. So vice versa will be done for the exponential functions, right? Let's graph a couple of more. So we've done base 2, we've done natural logarithm. So for this one, we're gonna do base 3 and base 10. So just quickly, just the parent, domain and range for all the parents ones are the same. So log in base 3 of x has the base 3. So the first point, because it's a logarithmic function, is gonna be with an x-intercept at 1. And the second one is gonna be the base, which is 3 and 1. So we have crossing at 1, and we have 3, 1. And we're gonna remember the shape is always an increasing graph from quadrant 4 to quadrant 1, like that. And with the vertical asymptotes, at x equals 0. And for all, if they're just the parent type, they're all going to be having the same dominant range, like I said. So x bigger than 0, y is a real number. Okay, now the bigger the k or the base is, the harder it is to sketch a logarithmic function in just a regular Cartesian plane. There's some weird looking sort of graphs that you can sketch logarithmic functions in. They're called logarithmic scales. Okay, so we would use those, but we don't really do that in our class. So I have here an example too, just the XY axis without the grid, because I'm going to do my own scale, so it's easier to see. For the purpose of sketching, that's all we need. So base 10, so you don't see the base, it's still there. I still would need 1. And then my next point would be 10, 1. So obviously I would need to fit here all the way up to 10. So if I choose here, this is my 10, I would choose here my 1, so it's a little bit easier to do. And then that's 5, and that's about 1 there, right? So the crossing happens there at 1, 0. And the next point at 10, 1. So definitely you can see I enlarged, I stretched the scale for y, so it's easier to sketch this function. And then we have our vertical axis. Let's fill in here that how graph is very steep. That's all I wanted you to have there. In between 0 choices for x's, this is for x, right? In between 0 and 1, and then after 1, the rate of change is lower. Any questions for the parent logarithmic function slash graphs? Does it have to be that spread out, like here? Well, if you don't spread it, like if you don't make the 1 higher, it would look very, it's hard to do the shape, because the shape always has to be something like that, okay? This kind of curve, okay? Now, when you have a really high k, if you cross here at 1, okay, and then let's say your k is 20, you have to have a 20 here, but then only 1 here, right? So it's going to be really hard to draw by hand something that's going to go in there, you know? So you're going to always make it look like this, and that's not true, right? It has to be a curve, right? That has this shape, but it's harder to do by hand. Okay? Even with the graphing calculator, it's really hard. A lot of the time, this piece, this tail here, it's merged with the y-axis. It's not visible. Even you have to zoom in to actually see that separation, right? That's how fast and how close it gets to that vertical asymptote. But yeah. So I guess the simple answer is you don't have to, okay, but then it makes it really hard to get. Okay. Any other questions? Oh, transformations. Your last transformation, the logarithmic ones. So A, if it's negative, we're gonna have, so if A less than 0, we're gonna have a vertical reflection, and then A in absolute value that's different than 1, you're going to have a vertical stretch or compression. Then B. If you have a B that's less than 0, you have a horizontal reflection. If your B is different than 1, you're going to have a horizontal stretch or compression. Remember to do the reciprocal. The reciprocal. Reciprocal. Too many L's there. And then now C. Horizontal translation, right or left, depending on the sign. And then D, vertical translation. Now for the logarithmic graphs, we had a vertical asymptote. So the vertical asymptotes will be affected by what transformation? That's right. So when you have a horizontal translation, that will give you your new vertical asymptote. So we will see that in our work for transformations. Example 3. Sketch the graph of y equals log in base 3 of x plus 2 minus 3 using transformations. The question on top of transformations says also include the intercepts and domain and range. Intercepts is maybe one that we will focus more. Domain and range you're really good at by this time. You know how to look at your graph and just read from the graph how domain and range is. So let's first deal with sketching using the transformations. So we're going to do y equals log base 3 of, writing everything in standard form. So log base 3 of x plus 2 minus 3, everything in standard form. If you don't like to include the type of function, which is log and base 3, then you can replace that with the name, right? Or with a name. What kind of name would you like to give log and base 3 of x? Sorry? F of x, sure, f of x is fine. So f of x equal to log in base 3 of x, our parent function, right? And then when we rewrite it, y equals, we don't write log base 3 anymore, we just write the name, f of, and now under the x, we don't just put x because that was for the parent function. Now we put what's under the x here, so x plus 3, plus 2, not 3. And then minus 3. And now it's a little bit easier to see the transformations without getting trapped there and sometimes thinking that base has to do with transformation. That's already part of the parent function. You don't have to include it again. So we have a horizontal translation 2 to the left, and we have a vertical translation 3 units down. So x minus 2, y minus 3. And this also tells you where your new vertical asymptote is. New vertical asymptote at x equals -2. Okay, so now the way I deal with the next parts, including the intercepts, I don't really include the intercepts after this kind of work. I like to sketch my graph and then do the algebraic work to find the intercept and see if it makes sense. I want you to practice doing the intercepts because all you do with intercept calculations is just basically doing exponential and logarithmic equation solving. You'll see what I mean in a bit. It's not hard. You already know how to do it. You just have to put it in that type of approach, right? Let x equal to 0 calculate for y, or let y equal to 0 calculate for x, okay? So let's see what we get for our graph. So we know that usually I start with the parent function and vertical asymptote of the new function. So log and base 3 of x we've done already. It's crossing at 1, and the next point is 3, 1. That's the parent one. The next point would be 9, 2. So it's going to be very flat right after. And the first transformation is translation to the left 2 units. And then that's why I want to have that vertical asymptote. So when I do these movements to the left, I don't want to cross that with the arms, right, with the ends of my graph. So then move to -1, and then move to here, right on top of 1. So that's my sketch. And the second one, move the graph up 3. The previous graph is the green one, move it up 3. And then up 3. Oh, down 3, that's right. Good catch. Thank you for not letting me write sketch out. I hate it when I have to erase my whole graph. Points is fine. Down 3. Okay, good job. And then down 3. And then we cross. Okay, so we got our transformed final graph. This is the graph of log in base 3 of x plus 2 minus 3. Some of you like to write that y equals, and then you write the type of function, x plus 2 minus 3. So because all the transformations are taken care of, right? So that should be your final graph. And we also like and should be labeling our steps. So step number 1, that corresponds to what we said we're going to do in step number 1. And step 2 is the last step, the vertical translation. Domain straight from the graph, domain is x bigger than the value of your vertical asymptote, so bigger than -2. And the range y is all the real numbers. So that's been taken care of. So I've done transformations, I've done domain and range. All I'm left to do is the intercepts. And once I finish all that algebraic work, I'd be able to look at my graph to notice, am I crossing the y-axis here where I should be? Does it make sense to get an x somewhere here to the right? Because my graph will end up to cross somewhere there, right? If you're getting, for example, an x-intercept somewhere to the negative, then you stop and either my graph is incorrect, maybe I forgot a reflection, right? The horizontal reflection, or my calculation is incorrect, right? So you have to take the hit in either of those places, because obviously it can't be both at the same time. Okay, so let's do it. The x-intercept, or maybe we should try start with y because it's a little bit more straightforward. The y-intercept, and that means we let x equal to 0 when we calculate y-intercepts, meaning we look at the original equation. That means here where x used to be, we put 0, and then we calculate for y. So the y equals log in base 3 of 0 plus 2 minus 3. Y equal log in base 3 of 2 minus 3. And then because we need our calculator to calculate this one and see if it makes sense, we're gonna convert the log and base 3 of 2 into what type of logarithm? Log of base 10 or log of base e, either or. You have to use the change of base formula. And that's, I guess, the easiest way would be to do the change of base formula. So log in base 10 of 2 divided by log in base 10 of 3 minus 3. And let's see what we get. And let's see if it's around the -2. So grab your calculator. Let me find my key as well. -2.36, you said?
This is without the rounding.
Yeah, it's fine, so about -2.4, that's fine. Okay, so does it make sense? Like approximately, that's okay, right? So it makes sense. We got the same value. Okay, Greg? Jenna?
Yeah.
Good? Good, okay. So makes sense, we keep it. Then for the x-intercept, what's the rule? We're gonna let what? Y equals 0, and then we're gonna solve for, attention at the word, the vocabulary. Here you let x equal to 0, and you calculate y, because everything on the right-hand side of the equal was given, right? You don't have to do any backwards calculation to get to the value of y. That's called calculation. Now here, when we're gonna let y equal to 0, we're gonna end up with an x that's missing, right? We have to do backwards work to get this. That's solving the equation, okay? So you have log in base 3 of x plus 2 minus 3 equal 0. That's a logarithmic equation. And you know how to do it. If you don't, give me a chance then to remind you. There you go. You move the -3 on the other side. And you have log in base 3 of x plus 2 equals 3. And then once we have a log equals a number, we can use the exponential form notation, right? So 3 comes around, pushes the 3 up. We have x plus 2 equals 3 to the 3. X plus 2 equals, what's 3 to the 3? Not 9. What is it? 27. Then x equals 27 minus 2, x equals 25. Does it make sense? X to be 25. See how slowly it increases? It's going to take a while. So it's going to get to 25, right? So yeah, but it makes sense. It goes in towards that. So it will cross at 25. Any questions? No questions? You good? So I'm doing one more transformation. I'm going to use points for this one. And then I'm going to do one with natural logs, just so you have one example with a natural logarithmic functions too. But basically, after example 3, I've shown you everything. Like these are all extra, examples, just so you can have more examples, but you don't really need all these extra examples. So sketch the graph of y equals negative log base 2 of -1/2 x minus 1. Close both brackets plus 3 using transformations, and then again include the following intercepts, equation of the asymptote, domain, and range. So y equals negative log 2. Notice log base 2 there. That's your type of function. So you can write. Who wants to name the function? give it a name. F of X, okay. Very creative. Okay, so then we're gonna have our function looking like this. Y equals negative is in front of it, negative. So now it's no more log base 2, it's f of, and notice how the transformations are visible because our equation is already in standard form, right? The b value is factored out, right? Separated from x, you have that binomial for reading your c value, and then you see clearly your d value. So what kind of transformation does a negative in front of f show us? Vertical reflection, so negative y. Okay, so how about the negative for the b there? Horizontal reflection, so negative x. How about the b that's a half? Stretch, because what we have to do is reciprocal of that, which is 2 times x. So it's going to stretch the graph horizontal direction. How about here, x minus 1, this minus 1. Where? Piece, in what direction? To the right, that's right. 1 to the right, so that means x plus 1. And then plus 3 at the very end, b value, vertical translation. This time it is up, 3 up. So x, not x, y plus 3. So by every point xy on the original function, I would have to apply the following transformations on the points. So for x, I have negative 2 times x plus 1. So these are all the x transformations. And for the y, you have negative y plus 3. Now, what are the points for the parent function log in base 2 of x? Because if you don't remember that, I would always try to do that first. I would try to remember how to do the sketch if I don't remember the points, and then I just put the points here because I can read them easily, right? Sometimes the visual approach is faster because your memory is faster if it's visual. So we know we have to cross at 1. We know, remember the shape, the increasing graph, quadrant 4 to quadrant 1. So we cross at 1, and then the next point is for base 2. 2 and 1, right? Okay. So we have our parent graph. Then it's 4 and 2. And it's 8 and 3, and so forth. So I'm going to only use these 2. We have the point at 1, 0. The next one at 2, 1. Negative 2 times 1 is negative 2, plus 1 is negative 1. 0 plus 3 is 3. Negative 2 times 2 is negative 4, plus 1, negative 3. Negative 1 plus 3 is 2. My vertical asymptote is at x equals 1. How do I know? I look at my horizontal translation. So I would start with that, especially when you're working only with points. You do not want to start sketching your points without a vertical asymptote because for sure you will cross it when you sketch the graph. And then we have a point at negative 1, 3. So negative 1, 3, and the point at negative 3, 2. So it will be something like that. That's right. Yeah. Yeah. Yeah, that's fine. Yeah. As long as you state it and it's somewhere on your work, yeah, it's already stated. Yeah. The equation of the asymptote is just saying where the asymptote will be, right? An equation will tell you clearly how to sketch it, right? So that's, yeah, that's it. Mhm. Now, we've done the sketching of transformations. We've done the asymptote. We can also do domain and range, and then we're going to focus on the intercepts. So the domain of our red graph is x is less than 1. So notice how for transform function, all of those characteristics of the parent function don't apply because this is not a parent function anymore. It's a transformed function. So you just have to look at it and describe its new characteristics. And then the range is all of the real numbers. So y belongs to R. Y-intercept. We let x equal to 0 calculate y. So y equal negative log in base 2 of negative 1/2, 0 minus 1 plus 3. Okay, now I'm going to teach you something. I don't think I ever told you this before, but now we're going to calculate for y, and you know what we're going to have to do. We're going to have to calculate for y. So yeah, I'm going to say out loud what I'm doing, but you guys get ahead of me. You know what you have to do. So keep going and try to, don't always raise your head up and down to copy what's on the board. Try to listen what I'm saying and actually follow your own thoughts, okay? And do the work that you are, we are supposed to do, because you know what you have to do. So let's get going, and you do it, and I'm doing it at the same time. So negative log in base 2 of, we're not going to write 0 anymore because there's no point of it, because 0 minus 1 is negative 1. And then plus 3, and then we're going to multiply those 1/2 and the negative 1 together. So work inside the bracket, positive 1/2 plus 3. We can then put the negative in the exponent. So log in base 2 of 1/2 to the negative 1 plus 3. We know a negative in the exponent is just reciprocal, right? So log in base 2 of 2 plus 3. Look how nicely this one cleans up. And then what is log in base 2 of 2 equals to? 1 plus 3 equals 4. The y-intercept should be at 4, exactly. Does it make sense? Look at that. Look how accurate we were. Pretty much at 4, right? When we cross the y-axis. There it is. X-intercept. So negative log in base 2 of negative 1/2 x minus 1 plus 3 equals 0. We have to solve this logarithmic equation. So my goal is to clean up here this standard form, because I don't need a standard form. I only needed it for transformation. And then I'm going to move the 3 on the other side, and then I'm going to try to get to a point where I can just go from logarithmic form to exponential form. So 1 log on the left, clean with no negative in front of it. So just a simple log with an expression under it equals a number. Okay. So negative log in base 2 of multiply through to get rid of the bracket inside there. So negative 1/2 x plus 1/2. And then move the 3 on the other side. So negative 3 equals negative 3. We can times now both sides by negative 1, or divide both sides by negative 1 just to get rid of the negatives here. So that I make it positive. Positive log base 2 of negative 1/2 x plus 1/2 equals 3. And now I have arrived at a single log equals a number. Now I can just write it in exponential form. Negative 1/2 x plus 1/2 equals 8. Here's a neat thing that I like to do sometimes when I work with fractions. I multiply by a common multiple, or the lowest common multiple, and that's going to get rid of every single one of the fractions, right? 2 times negative 1/2 makes it negative x, right? The 2 cancels out. Plus positive, right? 2 times 1/2 makes it 1, and 2 times 8 is 16. Negative x equals 16 minus 1. Negative x is 15, which makes x equals negative 15. Now we're looking at our graph. Does it make sense? Do we get to negative 15? Does that end of the graph approaches a negative number for my x? Yeah, right? It keeps going there somewhere along there. It will cross at negative 15 for my x-intercept. From this first step we did, when we multiply through, right? So this one was a bracket here. If we open the bracket, we have to do distribution, right? So times it by each of the terms. One more with natural log. Natural log of negative x plus 2 minus 4 using transformation state intercepts equation of the asymptote domain and range, just like before. The first thing we do, we can let, and I know, yeah, f of x equals equals ln of x, okay? And then we have y equal. There's nothing in front of the function, the ln of, so straight f of negative x plus 2 minus 4. We're going to notice that it's not in standard form, right? Why? The negative in front of x has to be factored out. So y equals f of negative bracket x minus 2, changes this sign for 2 because you're factoring out the negative out of both of those terms. And then outside, you can just leave it as negative 4 because you know the b value can be read exactly how it is, right? So this one we read as it is with the sign going in that direction, natural direction, and then if this one we go opposite direction. So we have a horizontal reflection, negative x. We have a horizontal translation, 2 units where? To the right, and then the 4 units down. So x plus 2, and this is y minus 4. From having a horizontal translation, we also know that the new VA is at x equals 2, right? So that's done. Parent function for the natural logarithmic function. So we remember crosses at 1, and then it's going to be E1. E is approximately 2.7, so there. Any point xy on the function, the original function f of x becomes the point negative x plus 2 and y minus 4. The point is going to be 1, 0, and 2.71. Remember, that's E. Now, for sketching purposes, you need the approximated value so you can get another point, right? So let's get going and calculate. Negative 1 plus 2 is 1. And then 0 minus 4 is negative 4. Negative 2.7 plus 2 is negative 0.7 approximately, and 1 minus 4 is negative 3. Vertical asymptote first, and then the points, and then the graph. That's 2. One, negative 4, right there. Negative 0.7, negative 3. There. And it looks like our graph is something like that. We can also read the domain and the range. Domain is our x less than positive 2, and range all the real numbers. So then, how is it less than 2? Because your graph is all to the left of the vertical asymptote. So all your x values are less than that number. So for every single point on this graph, my choices of x are always these numbers. They're less than 2. Okay? It would be bigger than 2, then your graph will be over here on the right-hand side. Let's calculate and solve for intercepts. Let's start again with the y-intercept. So y equals ln of negative x plus 2 minus 4. Oh, let's put a 0 there. Y equals ln of 2 minus 4. Get your calculators out and calculate it. You have a button for ln, so you don't have to do the change of base for this one. Negative 3.3 approximately. Good. Does it make sense? It does, right? We are crossing at that location. And for the x, it has to be a negative number, right? So we know what we expect for our x-intercept. So we let y equal to 0 and solve for x. So ln of negative x plus 2 minus 4 equal 0. What kind of equation is this? A natural logarithmic equation, right? So, but they're solved just like all the other ones. So I would move the negative 4 on the other side. We have ln of negative x plus 2 equals 4. Now I have a single log equals a number. I can write it as exponential form, but you have to remember the base is e. Otherwise, how do you go to exponent? You need a base, right? So negative x plus 2 equals e to the 4. And now this is the linear function, negative x equals e to the 4 minus 2. You can divide everything by negative 1. You get x equals negative e to the 4 plus 2. Even when you divide, distribution applies, just like when you multiply by a number, okay? So this divided by negative 1 and negative 2 divided by negative 1. Now, you know that e is 2.7. You can round it up to 3, just kind of like to make sure you got the right thing, right? 3 to the 4, that's 81, negative 81, maybe a little, not maybe, a little bit less than that, because we're doing the 2.7, right? And you add 2 to it, doesn't make a ding on it, you're still gonna be in a negative value here, right? So you could estimate some of these ones like that. You can even estimate your logarithmic values too, by using benchmarks, the same way we use benchmark for roots, right? So you place in between two known logarithmic values, right? And then you can see, okay, yeah, I am in between this number and that number, so yes, it makes sense for questions when you don't have a calculator. So just an FYI for calculations like these for tests, because I do let you have a calculator with you for just as a crutch, right? So don't panic. You still have to show all your work, right? Until you get to an exact value like this, and then if you need to use a calculator to get an estimate, then you would, okay? So that's done. We've done the intercepts as well. And this one approximately, I don't have it in my other notes, but you can just use your calculator. E is a button in your calculator as well. I think just around pi for my calculator. So you can see what you're getting. That should be a high number. So let's see. Put a negative as a negative number, that's minus. And then e to the 4 plus 2. Negative 52.6. Agreed? Right? Yeah? Jenna? Agreed, okay. That's right, yeah. It's hard to find.
Yeah.
All right, so that's that for transformations. Break time, 10 minutes. solving problems using exponential and logarithmic functions. There's a lot of real life events or phenomena resemble one of our exponential logarithmic functions. We're going to be looking at some problems using these models. So the first type that it's really widely used is the compound interest formula. When you borrow money or when you invest money based on an interest rate, that's called a compounded interest rate. The way that the money grows is based on this formula, where A is the amount at the end of a certain time period, P is the principal that's being invested, and then we have this 1 plus R over N as the base of a power, where R is the interest rate as a decimal, N is the compounding period, how many times a year that interest gets to be applied, and that N appears again into the exponent of that power, and T is time in years. So for us, because we're talking about exponential function, this is an exponent or a power, right? For this to be an exponential function, which part of this formula do you think it will be unknown? To be an exponential function. Which part will take the x or the unknown? Time, that's right, time, okay? N could not be because it also appears in the base, right? So you wouldn't be having it both ways, right? So the only thing really that could be the unknown here or the x would be time. So in these kind of questions, you would be using compound interest to answer the question, how long will it take for this and this to happen, right? For in this case, it's going to be money, right? For $1,000 invested in this account to become $10,000, right? How long will it happen? And you will have to know everything else except for time, okay? So let's have a look at example 6. If you put $5,000 in a savings account at 6% per year compounded monthly, how many years will it take to grow to 7,500? And then the answer needs to be rounded to the nearest year. So if you're investing, putting money into a savings account, meaning you're investing, or I guess it's a loose term, investing, you're putting money, you're saving money. $5,000 is what we call the principal. And then the 6% per year is the interest rate, but it's not the R in the formula. The R is going to have to be the decimal form of that. So 0.06, because 6% means 6 divided by 100, or 6 per 100. So 0.06. The way the interest is applied, it's called compounding. So compounded period is right here, right after the interest. So compounded monthly means 12 times a year. This 12 is the N in the formula. Compounding frequency. For your reference, in the box with the formula, I have other frequencies as well for other types of questions. So what does it mean to be yearly or annually? It's 1, because it's 1 times a year. What does it mean to be monthly? It's 12. How about weekly? 52 times a year. How about bi-weekly? 26 times a year. How about semi-annually? That's every half a year. That's 2 times a year. Semi-monthly, that means every half a month. That's 24 periods. So in case of other questions, make sure you're knowing those ones. But usually it's like the months that come in our questions. Okay, so now how many years will it take? So you know the question is T, right? The time. That's the focus. And then we want it to grow to 7,500. That's the A in the formula, the final value, the amount. So formula A equals P 1 plus R over N to the exponent of NT. Just plug in now. A is 7,500 equals principal 5,000. 1 plus 0.06 divided by 12 to 12 times t. Now, because this is an exponential equation, type 1 or 2, question for you. What do you think? Two, right? Because I mean, even if it was type 1, like you would have to go to extensive work to figure out what's the same base power, right? And check. So type 2 for sure, because the focus is not to solve it in the way of either of the types. So it's type 2, so definitely we would have to take log of both sides, right? And then you could be taking log of both sides in exactly the same form, but to make it a little bit simpler to calculate, I would first divide both sides by this coefficient by 5,000 to just not have anything in front of the exponential form, okay? So I choose to cancel the 5,000 here. And why do I want to cancel it and not have anything in the exponential form? Because when I take log of both sides, I don't want to have a log of a product, okay? Because then I have to apply the product rule, right? To split up the log, and it just makes it more work for me, okay? I don't want that. So by canceling this, it's going to give me less work. So 7,500 divided by 5,000, we get, is it 1.5? Yeah, 1.5. And we get 1 plus 0.06 over 12 to the 12t. Now we're going to take log of both sides. And here we will end up calculating this log, but at the very end, we will just have the expression, the finalized expression that we just plug into the calculator. Until we get there, we're going to deal now with the exponent or power law. We have a logarithmic expression with an exponent in the argument, so we can apply the power law to draft that exponent. And we want that because that's how we solve for that t eventually. So log of 1.5 equals 12 times t times log of 1 plus 0.06 over 12. So I wanted you to see that 12 and t are not glued together, there's times in between them. Because my goal now is to isolate t, and the only way we can isolate for t when we're solving equation is to apply opposite operation that reduces all the numbers around the unknown, right? So now t is connected with 12 and log of that expression by multiplication. How do we cancel multiplication? With division, right? So all we gotta do is divide left and right by 12 times log of 1 plus 0.06 over 12. So repeat over here. And you plug into your calculator. And you're gonna get what t is equal to. And that's what we plug in our calculator. There's some brackets needed there so you can get the right answer. So log of 1.5, close the bracket, divide by. Now open the bracket here. You might have to open another bracket here. That means at the very end, you have to close 2 brackets. You will have it on paper what the answer should be. So practice with your calculator and see if you're getting the same thing. Should give you 6.7746. So some interest or some growth, better said, happens continuously. And when we apply that trend into a continuous compounding situation, the formula changes a little bit. and it's not anymore dependent on the compounding because that's continuity. So you would have the formula of the previous one that we've done in this format, A equals P times E to the RT. So E is Euler's number. E is approximately 2.7, but we use our E button, our calculator, to use it in problems. A is still the final amount, not necessarily money, like usually is the money, but can be other things, can be population, for example. We'll do a question with population of golfers a little bit later. P is the original amount, and then we have rate again as decimal, and time is in any time units, because even though the growth is continuous, the time unit is referring to the rate. So we can always approximate the rate to a certain time period. So that time period is going to be the same. So these two, the time and the rate, are connected in terms of that time. So is it 1.5 a year? Then the time is going to be in years. Is it like 3.5 per day? Then it's going to be days and so forth. Okay. So connected, same time. So let's look at example 7, which is a similar example with the one that we've done. It's still a money problem. 2,500 is invested in an account that is compounded continuously. So notice the continuously word there. That tells you which formula to use for compound interest. If after 5 years the investment has an accumulated value of 4,000, at what rate was it compounded? Now notice that in this situation, the unknown can either be R or T, right? Because either of them are singularly placed only in the exponent, right? But meaning if it's R, like in this question, then everything else has to be given. If it's T for other questions, then everything else has to be given. E is not an unknown, is a known value. It's just like an irrational number, so we replace it with a letter, okay? So 2,500 is the principal. And then we have time is 5 years. We have accumulated value, the value after 5 years, which is the A amount, and the rate is the question. So what is the R? And the rate is going to be per year because the time is years. Make sense? Okay, so now we're gonna write the formula. A equals PERT. A is 4,000. P is 2,500. E to the R times 5, or 5 times R. So this is another natural logarithm, natural exponential equation. So in the end, I do want to take the natural log of each side, but to avoid applying the product law, I'm going to divide by 2,500 first. To eliminate that. So when we do 4,000 divided by 2,500, we get 1.6. And here on the right side, we're left with E to the R5, or R times 5. And I can take now ln of each side. I could take base 10 logarithm. That's not wrong. But when you take ln, we've learned last class, it's a little bit nicer, right? Because the ln of E cancels out to 1. So why not do that, right? So now on the right hand side, we have an exponent under the logarithm, so we can apply that power law. R times 5 times ln of E, and on the left we still have ln of 1.6. See how we ended up with times ln of E. Ln of E equals to 1, so we don't need it anymore. So now to get to R, all we gotta do is divide ln of 1.6 by 5, divide both sides by 5. So R is ln of 1.6 divided by 5, which is you should be getting 9.4 as a percentage, 0.094 as a decimal. Get to a percentage from a decimal, you just got times by 100. Make sense? Here's a question with the population of gophers. If the Winnipeg Zoo had 500 gophers on May 1st and the population grew continuously at the rate of 2.5 gophers per day, 5% of gophers per day, after on what date, so notice what we're interested on the date, but we do have to go to time, would there be 950 gophers? Okay, obviously this is an ideal situation for the growth of gophers, taking away predators, right? So being like just left to grow continuously at this rate, right? So a lot of the times in math, you're doing engineering, maybe in your future, or something like that, to be able to solve a problem in the real world, you have to take it outside of the real world and eliminate a lot of the variables, right? To focus on what you want to solve. And then you're going to put in the variables one by one into the real world and see how that affects your problem. Okay, so we have our principal, which is our original amount of gophers, 500. The May 1st is not important for the formula. It's just important later on to answer the question on what date. Okay, we just need the time, the number of days it will take to grow. We notice the word continuously. That means it's going to be using the compound formula for continuous growth, the one with base E, and then the rate is 2.5 per day. So we just want to make sure you have that into a decimal, so 0.025. And then we have the final amount of gophers, which is A. So A equals PE to the RT is the continuous growth formula. A is 950. P is 500. E to the 0.025 times T. The first thing we do to solve this exponential equation is divide both sides by 500. So 950 divided by 500 equals, what is it? 1.89. Okay, 1.9. And then we do what for natural exponential equation? ln, take ln of each side, and then drop the exponent in front using the product, the power law. So equals 0.025 times t, ln of e, just cross it over because it's going to equal to 1, right? ln of 1.9. And I divide both sides by 0.025. So this is going to give us the time, right? We don't want the time, we want the date. We just need the time to get there. So let's see what we get for time. I don't have my key for this page, so. Oh yeah, I do. But I don't have a key. What I do with it, I don't know. Let's see what you get. And then we'll find the date. Huh? No, I think it's a May date. But let's see first how many days. What's the time first? $3.6. Doesn't sound like it is, no. So you're gonna do ln of 1.9 divided by 0.025. So approximate 26 days, right? Make sense? So now, date. May 1st plus 26 days. So May 27th. Yeah. It's continuous. I don't know, I guess. And that rate is 2.5. Maybe the rate is off. Yeah, yes. I'm not sure how accurate this problem is. Yes, they're rodents. Those two types of questions were interest-based questions, so compound interest or continuous compound interest questions. And there's always other types of questions as well. For those other types of questions, the formulas that, or let's not call them the formulas, the functions they will use to get to the answer will be given to you, okay? So here's an example that, I remember doing these kind of questions in my chemistry classes, my first year chemistry class at the university. So for sure, you'll see them again, and you will have to calculate using these exponential functions. And probably that's why sometimes they do ask you to have a pre-calculus or calculus prerequisites before you take those classes. So you're not totally taken by surprise when you have to do that, right? A certain radioactive substance decays according to the formula. You have Y equals A times e to the negative 0.2x. It almost looks like, not almost, it is the continuous compound interest formula, right? But the values are given to you in the formula. So A is the original amount, Y is the amount remaining after X years. The only thing that's different here, it's not a growth, right? It's a decay. Therefore, that's why you have that negative there in the exponent, right? It's going to decay. It's going to slowly have less and less amount of the original substance. So the first part of the question says if A is 80 grams. So if you start with 80 grams of this formula, with this substance, how much is it left from it if it decays after 3 years? The first one, since you know every single thing on the right-hand side of that formula, that means all you have to do is calculate for Y, right? So this one is calculate Y. So Y is 80 e to the negative 0.2 times 3. So you gotta take your calculator and make sure you know your E button is and just type 80 times e to the exponent of negative 0.2 times 3. Make sure the 3 is in the exponent as well. So you might need a bracket. If you do this button, you might need a bracket here, or just calculate the negative 0.2 times 3 to be negative 0.6. That might be okay too, or easier. And we should get 40 something. What was it? 43.9. So almost half of the original substance. I would call this one a highly radioactive substance, right? So if you start with, I'm going to give you a stupid example, but if you start with iron, and after 3 years, you only have 43 grams of iron, and then the leftover is something else, right? That's highly radioactive. It became something else, right? It changed its form, and all the properties of it, it's changed, right? That's really what happened. That's why it's dangerous for us to be around radioactive substances. So for B is, what is the half-life of the substance? Half-life is a term they use for deciding what's a highly radioactive substance and what's not, right? So the faster it takes for something to change its, to change into something else, the more radioactive it is, right? So what is the half-life of the substance? So how many years will it take to get half of the original substance? We know the original substance was 80 from the previous question, but we didn't really have to use the 80. We just know it has to be half of an original amount. So if I say the original amount is 2 grams, okay, then at the end of a certain amount of years, the half-life, right, the new amount after some time, it has to be half of it, because that's how we define half-life, right? It happens in amount. So all I gotta do, so this would be my the A, right, in the formula, and this is your Y in the formula. So you gotta put 1 equals 2 times e to the negative 0.2 x, right? And you're searching for the half-life, the time. So this is just like any other exponential equation we've done so far. So divide by 2 to eliminate that little problem. So we end up with e to the negative 0.2 x equals 1/2. Take ln of both sides, because the base of this power is e. If it was another power, like 10, let's say, for pH problems, you would choose log, because that simplifies quite a bit. And then we're going to drop the exponent there. And ln of e disappears because it equals to 1. 1 times x is still x, so that's why we cross it over there. And then to isolate for this x here, we have to divide both sides by negative 0.2. So ln of 1/2 divided by negative 0.2 gives us our half-life. It should be about close to 3 years, because the other one started from like 80 and ended up to 43 grams, right? So that was almost half. .47, 3.47. So just a little bit over, we can say about 3.5 years, right? I don't think I have another question if you're notes. This was it. And you're done.